Hi, everyone. Let's get started on time. This is the first of the CoolSci series this year, and we are celebrating today the accomplishments of our 2025 STScI Achievement in Astronomical Research Award winners. So today we're going to hear from Marco Chiaberge, sorry, Steph Lamassa, and Mark Rafalski. So the format today is going to be the presenters have 17 minutes and then followed by 3 minutes of questions. And then we will adjourn at 4 o'clock for champagne and cookies in the Cafe Con. So Marco, you want to get started?
All right. I hope you guys can hear me. This morning I woke up with no voice, so where's my... This one. All right, let's go. Okay. So thank you for showing up today, even here in person, either here in person or online. I want to thank the Science Evaluation Committee for this award. I know it's a lot of work for the committee, and it's great to be recognized by a committee of my colleagues. So this really means a lot to me, so thank you. I also want to thank my collaborators, because it is obvious to say this, but I wouldn't have been able to do all I'm about to talk today if it wasn't for them. I think that some of them are online and some are in the room, so thank you to them too. And the title of my talk is From Black Holes to Human Health, Keeping Astronauts Healthy for Long-Duration Spaceflight. And I will focus more on the second part of the title, because that's what the SEC highlighted in my science evaluation. But let me start with this. Okay, so this is another work we have done last year. I've done it with these people whose names you can see down here, and some are in the room. And it is about a quasar, 3C186, which is a quasar at redshift 1. It's hosted by a giant galaxy at the center of a cluster. And we've been working on this for a while, but basically, what we think now, and in this paper in which we use the spectra from Subaru and VLT together with some HST data, we are pretty sure that the quasar is, first of all, off-center, because it's not at the center of the host. The center of the host is here, the quasar is here. And it's also, we have spectra that show that the quasar is moving with respect to the host galaxy. This is a talk for another time. I'm not going to talk about this, but the reason why I'm going to, even if it's interesting, but the reason why I'm showing you this is because it would be, it's a quasar in which the black hole has a mass of about 10 to the 9 solar masses, and it's at redshift 1. So it would be really cool to be able to resolve the sphere of influence of these black holes pretty much at all redshifts. And if we want to resolve the sphere of influence of this black hole, which is probably about 100 or the order of 100 parsecs, then we need a telescope that is at least 20 meters in size, diffraction limited in the optical if we want to do this, and so ideally in space. And this is really where the synergy between astrophysics and the other activities related to space exploration that NASA has been doing for a while now are really important, and I really want to highlight those. We are all familiar with the service missions where astronauts helped to, well, fixed the Hubble telescope a few times, and I participated not in space, but from here in one of those. So we're all familiar with this, and I think that in the future, future giant telescopes will be not launched as they are, built on the ground and launched in space, but they will be assembled in space, possibly by robots and humans working together. And so I took the freedom of making a funny video that I hope it works. About, oops, yeah, of course it doesn't. with AI, and you can tell it's AI because this is a telescope assembled around the moon near the lunar gateway or something like that, and you can tell that it's AI because the moon has a lot of atmosphere, of course. and also, I'm not sure about handling a mirror like that, but also it gets like split into different sections. But anyways, this is how I imagine things may happen in the future with humans and robots working together to assemble these giant telescopes. And this is more like sci-fi, but there are actually already some ideas about piggybacking on Artemis on the moon. And I only want to cite two. This is the Lunar Crater Radio Telescope. It's a project for a radio telescope on the far side of the moon where there is no radio emission from the Earth that can bother long wavelength radio detections. And then there's this other interesting Artemis-enabled stellar imager, which is a lunar long baseline optical UV imager interferometer. And this is something that could be potentially built near the Artemis base. So again, by a collaboration between robots and humans. HWO and future NASA flagships will be serviceable. And full robotic servicing, the way we saw in service emissions, is still not possible. So either you make it so simple, to quote John Gransfeld, so simple even a robot can do it. But then it's hard to predict exactly where telescopes break. Telescopes are complex machines. So I would say that probably humans, at least at some level, will be needed during a future service emission. But human spaceflight is hard. And this is the 5 risks that the human research program at NASA identifies. And this is just a list of 5, but each of these has a huge number of sub-risks. Space radiation, we're not used to that, thanks to the atmosphere. Isolation, in space, you're alone. It's a hard environment. Distance from Earth. You probably read that the astronauts from the space station are coming back today because of a medical issue. And when you're on the space station, it's easy to come back quickly. If you are on the moon or around the moon, coming back quickly for a medical issue is more problematic. Hostile and closed environment. So when you are inside, it's a hostile closed environment. When you are outside, it's a hostile environment as well. And number 5, which is what I will talk about from now on, is reduced and microgravity. So what does reduced or microgravity does? Reduced gravity is on the moon, for example. Microgravity is basically zero gravity in the ISS or any other orbiting stations. Spaceflight exposes the human body to microgravity and radiation environment, and that has a negative effect on the human body in terms of muscles and bones. Muscles undergo atrophy and bones become weaker. So countermeasures have been developed, and they are continuously updated to help astronauts. But it's not enough. About 20% of it's a combination of 20% of the astronauts that go back and those that come back to Earth have a 20% atrophy in the muscles or some other sorts of problems after they come back, even if they work out about 2 hours a day every day. So what they do is they bike. As you can see, this is a stationary bike on the ISS. There's no seat, which is weird, but you don't need a seat in space. They run on a treadmill. And they do strength training with this machine that's called the ARED, in which they can do all sorts of squats and deadlifts and other things. These machines are heavy. So if we want to use these kind of machines to go to Mars or even on the moon, you can't really put them on a smaller station. They're okay for the space station, but not for a smaller spaceship. So we need to find something else. So how and why did I start MJ? MJ is the name of the project. It stands for Mice Jump. You will understand later why it's called this way. I started it because I've always been interested in in exercise science and physiology at the level of a hobby, at least until I did this. And so I was reading from textbooks and some science papers, and I ran into this sentence. Current understanding indicates that human cartilage undergoes atrophy or thinning when external loading is removed. And this was in the framework of post-operative immobilization, where people need to stay in bed maybe for long periods of time, months. And what they found is that after that, they showed the beginning of osteoarthritis in their knees. So cartilage, for those of you who don't know, it's this layer of tissue that covers the bones at the joints. And it basically ensures that you can move your knee smoothly without any pain or any sound. And when this starts thinning, then we have osteoarthritis, and then it's a problem. It's painful, and it's bad. So I started looking because I immediately, being exposed to service emissions and being interested in space exploration and working here, I was like, okay, so astronauts do not load their joints when they are in space, and if we want to spend longer periods of time in space, this is a problem, right? So I started researching, and I realized that cartilage loss in space is an unmitigated risk, but it's also understudied. It's not really studied as much as, for example, muscle atrophy or the effect of microgravity on bones. And also, we don't really know what to do, because if you look at the knees of the cartilage in the knees of athletes that load their joints all the time, much more than a normal person, that is not thicker. So we don't really know what is the good effect that we can, what is the good type of exercise that we can do to help astronauts. And this is a normal knee. It's an X-ray of a normal knee. This is an arthritic knee. So if this happens, where the spacing is reduced, if the astronauts develop arthritis, they have pain, they have reduced mobility, there is higher risk of fractures, and they cannot work out to keep their muscles healthy. So they cannot stay in space for a long time. And we don't know how much gravity is needed. Maybe the lunar gravity is not enough. We don't really know. So long duration space flight, for example, to go to Mars may be extremely difficult. With the current technology, it would take about a couple of years to go there and come back. Forget it. And this is just a small problem. There's a lot more problems in human spaceflight, but we decided to focus on this. So current exercise protocols do not address cartilage health, and we must come up with something. So I started talking with these people because they were at Hopkins. They are at Hopkins, some of them at least. Colin Norman in particular, that you all know. Mark Schellheimer is at the medical school, and he used to be the chief scientist for the NASA Human Research Program, so he's an expert of human spaceflight. And Fan is at Carnegie and JHU, and he's the biologist in the team. He's in the room, so thank you, Fan. Joe was a graduate student in biology at that time, was a friend of mine, so we started brainstorming, and then later on, we included more people, engineers and others, and the students, Anderson, Christine, Dylan, and Ilima as a postdoc. They did an amazing job. Some of them are real experts of sports science. Anna Maria and Anya work with ESA and NASA on this problem of cartilage degradation in space with astronauts. So we have a full team. I wish I had more time to tell you more about them, but I have to run. So MJ, mice jump. So what is the hypothesis? We had to come up with a new type of exercise that the astronauts are not currently doing, because they, as I told you, they bike, they run, they lift weights with this strange machine. What they don't do is jumping. And there are reasons for, when I started looking into this, I realized that there are reasons for thinking that jumping could be a good way of stimulate cartilage health. So plyometric jumps is basically an exercise. It's a power exercise. So I show you here, there's a guy that jumps on this box. And basically, it's an explosive exercise that enables a muscle to reach maximal force in the shortest period of time. The reason why we think this may work is because there are some studies showing that cyclic compression on cartilage explants stimulate protein synthesis. And so if that really works in the lab, maybe it also works in humans when we compress the cartilage in the joints by jumping. How can we test this? We can't really do it with humans first. So what you do in biology, when you want to test something that potentially works on humans, you first work with mice. That's one common way of doing it. But the problem was there's no commercially available apparatus to make mice jump in a controlled manner in a lab. And so the first thing we did is we built one. And we got a small grant from Johns Hopkins, Space at Hopkins, so thank you for that. And we went to the JHU IDG lab just across the street in the physics and astronomy department. And together with Steve Smee and Steve Hope, right here, and Anderson Furlanetto was our student at that time. He's at Northrop Grumman now. They're all super successful now, these guys. So we built this machine, and this is the final version of it. I don't have time to tell you how it works. Basically, you put the mouse in here, and then there's two motors that bring two platforms up and down, and the mouse just jumps jumps up as many times as you want. And then we said, okay, we need to prove that this works because we need funding, right? And so let's do a test experiment. And thanks to Fan and his lab at Carnegie, we got some funding for that in 2022. And we thought, okay, let's show that we can do this. We don't really care about the results. And so we had 3 mice groups, small groups. One group was hind limb suspension. So these are the real space mice. They don't experience gravity on the hind limbs, but they can still walk around and do their things in the cages. And this is done with the NASA standard hind limb suspension method. Then we had the jump group. The mice were jumping 3 times a week. These are 5 or 6 more mice that were jumping 3 times a week. And then we had control, just mice staying in their own cages. And this is a picture of the MJ apparatus in the lab at Carnegie. And then we looked at the results. We did micro CT scans in Aaron James's lab at the medical school. And we went to, this is the machine that is done to do CT scans of tiny things like mice legs. And what we did was to measure the thickness and the volume of the layer of cartilage at the point of contact. This is the tibia, and this is the femur. And so we went to the medial side of the tibia, and we measured the thickness here and the volume. And we were absolutely not expecting to see this. So these are the 3 groups. This is control. So the green one is normal. They do nothing. The mice did nothing. They just walked in their cages. The hind limb suspension mice, we were expecting to see a negative effect. So the cartilage got thinner. And this was basically, we reproduced a study that was already done years ago by other people. So this is something that we expected. What we did not expect was that the group of the jumping mice were up here. And this is a 25% increase in thickness and 40% increase in cartilage volume. That was a very high statistical significance, and we weren't really expecting this. So this was, I think, an important result, and we got to write a paper that was published in this journal, part of the Nature group. So we were happy about this. So what's next? We need to validate the hypothesis, because what we did so far is a group that jumped and a group that is suspended. We need to combine the 2 things and show that at the end, if they jump and they are suspended at the same time, the cartilage thickness is the same as the control. This we haven't done yet, but it's important. Then we need to compare with other exercise modes, like running and strength training, stuff like the astronauts do. We are already expanding the research to humans. Me and some other people are collaborating with the Aerospace Medicine and Rehabilitation Lab at the University of Northumbria in the UK. We will use this machine. It's a new machine that is made by this company, Physical Mind in London, and allows for jumping in space. Yeah, we hope that by studying the biomarkers of cartilage degradation in a group of humans jumping in this machine, we can see something like that. Okay, my conclusions. First of all, this was the best part. I think like seeing people working that are experts in different fields, working together on something that they have never done before, because we had the expert of mice, but he never worked on astronaut health. We had the expert on astronauts that never worked with mice. Me, I never worked with any of this, but I came up with the idea, so I had to learn everything, and it was amazing. And so multidisciplinary research facilitates innovation and creativity. Jumping exercise improves cartilage health. We see also positive effect on bone structure, which is great for astronauts as well. And these are promising results for astronaut training. Let's build big telescopes in space. And probably this may help people with osteoarthritis in hospital, patients on Earth. And so this is great. We got to publish this paper that got a lot of attention. We are in the top 5% of the research papers tracked by Altmetrics, so that is great. We also got a lot of articles that make no sense in the press, but that is also part of the game. So this was a lot of fun. I hope you had fun too. Thank you for your attention.
Thank you for that great talk, Marco. So we actually don't have time for questions, so we're going to have to move on to our next person.
Come see me when I'm drunk.
Yeah, give me that. It's off. Okay, thanks. Well, it's probably better. And okay, hopefully the mic is on, y'all could hear me. All right, so we know that supermassive black holes, millions to billions of times the mass of our sun, live in the center of every massive galaxy. Most of the time, these black holes are dormant, but when material gets too close to the gravitational pull of the black hole, it can't escape the gravitational forces. That material starts spiraling into the black hole, losing angular momentum and forming an accretion disk, by which the black hole grows in mass. When we observe a supermassive black hole that is being fed by a steady supply of fuel from an accretion disk, we call those objects active galactic nuclei, or AGN. And they're some of the most energetic objects in the universe. And because of this, we can see these growing black holes from our cosmic backyards to the edges of the universe. So studying AGN gives us the ability to understand how supermassive black holes grow and evolve over cosmic time. And it also seems clear that they play an important role in galaxy formation and evolution. And one observational piece of evidence that suggests that this is the case is a correlation between the properties of a supermassive black hole and the galaxies in which they live. In this case, this is a correlation between the mass of the black hole and the velocity dispersion of stars in the bulge of a galaxy. And at first glance, this correlation over several orders of magnitude is surprising because the size and the mass scales between the black hole and the galaxy are different by orders of magnitude. This correlation is then indicative that there is a physical link between the black hole and the galaxy. And we see from some theoretical modeling that you need energy output from a black hole to slow down the growth of galaxies. AGN provide a number of emission features across the electromagnetic spectrum that we can use to identify which galaxies are harboring growing black holes. But what we actually observe depends on a couple of properties. How bright that AGN is compared to the galaxy in which it lives, and whether or not that AGN is embedded in large amounts of dust and gas. For an unobscured AGN, we have a direct view to that central engine of the accretion disk feeding a supermassive black hole. So we will see bright ultraviolet and optical emission from the accretion disk. And this is from material getting really hot due to friction, releasing a lot of energy. The photoionization of the accretion disk energizes its surroundings. And we see gas that's near the black hole that is orbiting rapidly, so we'll see broad emission lines in the spectra. And even out to the galaxy, if the black hole is powerful enough, we can see these very strong narrow emission lines due to the AGN photoionization. There's a corona of hot gas around the accretion disk that inverse Compton scatters the accretion disk photons into X-ray energies. And according to the AGN unification model, there is a torus of circumnuclear dust that's about the scale of a parsec that absorbs photons from the accretion disk and re-emits in the mid-infrared. Some AGN are obscured, which means we don't have a direct view to that central engine. They could be obscured from dust and gas in the host galaxy, or more often that obscuring torus from unification models. So here we don't see emission from the accretion disk. Even X-ray emission can be attenuated. And we can see some strong emission from that circumnuclear torus that is re-emitting that optical and ultraviolet light from the accretion disk. These obscured AGN are more challenging to identify, but they are a really interesting population. And it's something that I've been interested in since I was a grad student across the street getting my PhD. Most AGN are obscured. So if you want a complete picture of black hole growth over cosmic time, you have to make sure you know about this population. And some obscured AGN might represent a short phase that is an important link in supermassive black hole and galaxy coevolution. And in this picture, you have some triggering event like the mergers of galaxies that stir up lots of gas and dust to the center of a galaxy, which then ignites circumnuclear starbursts and turns on the AGN. At this point, the center of the galaxy is very obscured due to the dust associated with that circumnuclear starburst, until powerful winds from the AGN evacuate that surrounding material, revealing an unobscured AGN that we could find easily in large area optical and ultraviolet surveys. So if we can find AGN in this phase, then we could have insight to a key piece in galaxy evolution. And this could be something that gives rise to the M-sigma relation that we observe. And this is a population we're just starting to understand. It was this gap in our census that my collaborators and I wanted to address with the wide area X-ray survey in the STRIPE 82 region of the Sloan Digital Sky Survey. We wanted to do an X-ray survey because X-rays are the most efficient way to detect AGN. Normal star-forming processes aren't going to produce X-ray emission above a luminosity threshold of several 10 times to 42 ergs per second. We wanted to go wide because that's the only way to detect a statistical sampling of rare objects that have a low space density, objects like high luminosity AGN. And though high luminosity AGN are rare, they are important. According to many models, the majority of black hole growth happens in a phase where the AGN is luminous. And as we've just talked about, the obscured luminous population might be key players in galaxy growth and black hole coevolution. So STRIPE 82X is 31 square degrees, which I know compared to many surveys like Roman, doesn't sound very wide, but recall that most surveys with Hubble and JWST are measured in arc minutes, maybe a couple of square degrees. When we started this survey a whole bunch of years ago, in 2010, there were no wide area X-ray surveys. We were among the first. And so we wanted to complement what we already had on the ground from surveys like Sloan Digital Sky Survey, and from space and the infrared with WISE. And we chose the STRIPE 82 region of Sloan because it's a legacy field. It has a ton of multi-wavelength data, it has deep imaging, it has a lot of spectra. When you're doing an X-ray survey, you really need the supporting information to identify the sources that you're detecting and to characterize them. So there's a whole bunch of science that we wanted to do, and we did with Stripe 82X. We wanted to understand the X-ray view of high luminosity AGN and compare that with what we already learned from the optical and the infrared. We wanted to quantify the obscured AGN fraction at high luminosity, high redshift, and how that evolves over time. We wanted to understand the impact that these AGN have on their environments, as well as quantify biases in AGN selection functions, because again, you can identify these things at many different wavelengths. We used data from the XMM Newton and Chandra observatories for the survey. We were awarded XMM data in cycles 10 and 13 to build up X-ray coverage in the stripe. And then we supplemented that with archival data from Chandra and XMM that already existed. And since the beginning, we were doing an extensive ground-based observing campaign to get spectroscopy of the sources that we were identifying. And after completing 2 of these observing campaigns, we reached a milestone with our survey that culminated in our 3rd data release that we published in late 2024. So in total, we have spectroscopy for over 55% of our sources, and a third of that came from our follow-up. And we have photometric redshifts for most of the rest of the sources. This is the luminosity redshift distribution of the AGN in our surveys. We also detect a bunch of stars. M dwarfs are really good at giving off X-rays. If anyone's interested in M dwarfs, come see me. Our biggest contaminant. Because Stripe 82X is a wide area shallow survey, we preferentially identify the more luminous AGN. So our median X-ray luminosity is around 10 to the 44 erg per second. In our latest catalog release, we also calculated black hole masses for the unobscured AGN. There are about maybe 1,200 to 1,300 of those. And we took a look at the accretion rate of these black holes that's quantified by the Eddington parameter. So this is the bolometric luminosity of the AGN divided by the Eddington luminosity. And we find that most of these AGN are accreting at levels below 10 to 30% Eddington. And then we looked at the accretion rate as a function of the X-ray luminosity of the AGN. We found that the ones that were most rapidly accreting are hosted in the AGN that are most luminous. This is consistent with that picture that most black hole mass accretion happens in a phase when AGN are luminous. And if you want to know about these types of sources, if you want to know about when most of the black hole mass accretion happens, you need the wide area surveys to detect enough of these sources to really understand what's going on. Our collaboration has done several studies with this data set to better understand obscured black hole growth at high luminosities. Alessandro Pecca, back when he was a grad student at the University of Miami, corrected our sample for biases due to various selection effects to derive an intrinsic obscured fraction based on the amount of X-ray obscuration. And what is shown here is the fraction of obscured AGN as a function of redshift for 3 different luminosity bins. And we see at every luminosity, the fraction of obscured AGN increased with the redshift, but it also decreases with luminosity. And for this highest luminosity bin, between 10 to the 45, 10 to the 46, all the way on the right, this is where we really need surveys like Stripe 82X, because other surveys are not large enough to detect enough AGN at these luminosities for this type of analysis. Connor Agee, when he was a grad student at the University of Miami, looked at the spectral energy distribution of X-ray identified AGN and tried to understand how those correlated with different AGN properties. For this, he used data from Stripe 82X, as well as data from other surveys that sampled different portions of the luminosity redshift parameter space shown in the plot on the left. So he used data from Cosmos, which is medium area, medium depth, data from the Chandra Deep Field South in GOODS, which is the deep pencil beam survey. And what he did was to divide the sample into panels that were defined by the spectral shape, and to calculate a median SED for each of these panels. So as we go down these panels, the ultraviolet flux decreases, and the bottom 3 panels are defined by differences in their infrared spectral shapes. And he said, okay, so for each of these SED bins, what are their average properties? So first he looked at the luminosity and found a clear trend that the ones that are most bright in the ultraviolet are the most luminous, and this is the bolometric luminosity. And then he correlated the median SED shapes with the amount of X-ray obscuration, parameterized by the column density. And again, found that the ones that are the brightest are the least obscured in X-rays, while the ones that show more UV attenuation also are more obscured in X-rays. And he suggested that perhaps this is evidence of an evolutionary paradigm where these different SED shapes are pointing to AGN transitioning during different phases, where maybe you start more obscured, you have some winds that clear out the obscuring material, and you have your unobscured AGN. So in addition to quantifying the evolution of obscured luminous AGN, we've also used this data set to learn about the effects that AGN have on their environments, understanding selection biases at different wavelengths. We released an updated catalog, Stripe 82XL. So this includes additional data from XMM and Chandra archival data that became available in the field after we published our initial catalog release. There's plenty of other science that could be done, so I encourage you to think boldly about any fun ideas and to use the catalog to go ahead and play with those ideas. And I'd like to close by spending a few moments touching upon the award citation that highlighted the public outreach efforts that I do. Since 2018, I've had this awesome opportunity to participate as a panelist in the space track for DragonCon, which is this large annual sci-fi convention in Atlanta, Georgia. I go there on vacation and I give talks and a bunch of panels. It's a very weird way to spend your vacation. It's a lot of work, but it's so much fun. In 2024, I was on a panel celebrating 25 years of the Chandra X-ray Observatory. And this was a panel idea that I pitched with my friend and colleague, Roy Kilgard, who's shown on the right. Roy and I used to work in Chandra mission support many, many years ago. And rounding out our panel in the middle is astronaut Katie Coleman, who was on the Space Shuttle Columbia crew that launched Chandra into space. So for us, for both Roy and me, this was like a career highlight to be on a panel with an astronaut that launched an observatory that launched our careers. So I know when I give these public outreach talks, what I represent is beyond just me and the work that I do, that I'm a representative of STScI and the astronomy community to the public. And what's amazing about these experiences is that I get to see firsthand the impact that all of our work has on the public. How we're uniquely positioned to bring a sense of awe and wonder into the world. I know that we're going through some really challenging times right now with the national science funding, but it's also clear that the missions that we support at STScI have a future, and that we are going to continue to enable scientific discoveries and support the astronomy community and inspire millions of people around the world. So I want to thank you for the opportunity and privilege to be a part of all the great work that we do at Space Telescope. And I'll leave it here and take questions.
A couple questions for Steph?
Yeah, really interesting stuff. Does having the X-ray and the mid-infrared let you say anything about the geometry of the dust and opening angles and things of that sort?
Yeah, so I think to do that well, you would need more detailed data than most of the data that we have, because it's mostly photometry. In Alessandro's work, he did fit the X-ray spectra to derive column densities, but I mean, when you only have like 20 photons, how much do you really trust those column densities? There are some interesting results that have come out of that. One of the things that we did that I didn't have a chance to talk about was a survey that we did with Sloan to do spectroscopic follow-up of a bunch of our X-ray sources, and we also put fibers on AGN from Ys that have Ys colors that say they should be AGN. And a couple of interesting results from that paper published in 2019. And one of them is that there's, you always hear that infrared selection should get you all the luminous AGN. There were a whole bunch of luminous X-ray AGN that were not detected by Ys. So we started looking into that to see whether or not these could be like some weird like hot dust poor quasars, and see how that kind of fits into the global picture. We started the project, we haven't completed it, but to me that was kind of interesting. It's like this anomalous result we weren't quite expecting. Was that telling us about what the geometry of the torus could be? Another interesting thing that we did in the most recent paper was kind of like this Venn diagram overlap of different classes of obscured AGN. So you have the type 2s where you don't see the broad lines. You have the X-ray obscured, which is just based on the X-ray column density. You have the ones that are reddened, and you look at the overlap, and there's not much overlap. So what's that telling us? So nothing that I could say yet, but I think I would hesitate to say that there's any global results. I think it's complicated, and I could imagine there's different subclasses that could be telling us something interesting.
I think we have time for, yeah, Rachel.
I'm not surprised that M dwarfs are producing lots of X-rays.
Yes.
But do you have a sense of how extensive was the contamination from M dwarfs?
Oh, do I have that in here? It was something, I mean, it's under 10% for sure are stars. There is a version of the talk, and I don't have that slide in my backup. Do I? No, I don't think I do. Where I break out the classification. It's I want to say 5-ish% maybe of stars, okay. But I have to double check that.
I think we have to move on. Let's think step again.
So today I'm going to talk about the baryon cycle, and I wanted to thank you all for this opportunity to give this talk. But in particular, I wanted to thank all the postdocs and students who did the majority of the work I'm going to present today. I think many of these faces are familiar to you. Greco, Mitchell, Alex, Kalina, Ilias, Faran, and Emmy. Emmy is a student you may not know. But thanks to all of their work and the work of a lot of my collaborators not listed here, all of this was possible. So the reason I'm talking... I hope you like my version of your figure. So the reason I'm talking about the baryon cycle is it connects a lot of the different areas of research that I'm interested in. And the baryon cycle really is about gas flows and star formation, right? You've got diffuse gas everywhere, and then you've got more concentrated gas in the cosmic web, which is accreted onto galaxies. Those galaxies form stars with that gas, causing outflows, and depending on the potential well of the galaxy, that gas is accreted back on via recycling, and that's the baryon cycle. But this is a very hand-wavy, skipping a lot of the details description, similar to the spherical cow analogy. And this is going to be plenty for you all to understand my talk, but there's a lot of details that I'm skimming over, and it's really just a spherical cow of the baryon cycle. And today I'm going to talk about the mass-metallicity relation, and that depends on these gas flows because the efficiencies of the outflows and inflows change the shape of the mass-metallicity relation. I'm going to talk about the orientations of galaxies relative to background quasars, measuring the gas, and how that can provide evidence of gas inflows and outflows. I'm going to talk about the association of galaxies and damped Lyman alpha systems. And these show that damped Lyman alpha systems are composed of primarily the circumgalactic medium. And then we're going to look at some of those properties of that gas, showing the H1 mass density. And for the first time, we're going to show that that actually turns over and peaks at a redshift of around 3, as well as look at the metallicity evolution with redshift. And then I'm going to end at reionization because, and what does that have to do with the baryon cycle? Well, the galaxies are believed to have reionized the universe. The baryon cycle produces the galaxies that did that. But in addition, the CGM gas and the IgM gas affects how much was able to be reionized and how we're able to see those galaxies that have reionized the universe. So first, I'm going to start with the ISM of the galaxies, interstellar medium, and the mass-metallicity relation. So this is just a cartoon of that. On the right, we've got the high masses. There, the outflows aren't that important, but what's really important are large inflows and significant enrichment from a lot of star formation. And those kind of balance out and create this flat part. And then as you go down to lower masses, outflows play a more and more dominant role, and you have less star formation, so less enrichment. And so you have lower metallicities. But at any given mass, depending on the gas coming in and reducing the metallicity of that system, you're going to have a different position on this diagram. And so somewhat counterintuitively, higher star formation rates are caused by more inflows, actually have lower metallicity. Okay? So what are we interested in? Well, how did this change with redshift or over time? And what do you see if you go down to even lower masses? Does this turn over or not? And so one way we're going to look at that is with the MUSE Ultra Deep Field. This is a special field which has 2 quasars at a redshift of 3. So these we can use to measure the gas in the foreground to those quasars. It's got 142 hours of MUSE, so this is the deepest field with MUSE on the sky, allowing us to measure the galaxies. And then we've got 90 orbits of WIFC-3 IR GRISM, helping us get the near-infrared view of those galaxies. And we've got 5 filter imaging. Now, if you look here, there's 2 colors in these histograms for the redshifts on the left there. I'm only going to talk about the high redshift part because of time, but I do want to point out that we go to very low stellar masses and very low star formation rates. Okay, so I'm going to jump right to the result, which is the mass-metallicity relation. The black line is the redshift 0 relation. And then the blue points are the new measurements from the MUSE Ultra Deep Field. The red points are from a study from Elena Henry and me from a few years ago. And we've combined those and fit the blue-red dashed line. And this is work by Mitchell Rowalski showing that there's an offset in normalization and metallicity with redshift from redshift 0 to 2. But we don't see any significant changes in the shape, even as we go down to very low masses. Right? Now you might ask, well, I thought I heard JWC finds a change in the low mass slope, right? What's going on here? Well, first of all, mostly that's at higher redshifts, so maybe there's redshift evolution. And that could also be due to choice biases in star formation and so forth. So we want to say, is there evolution with redshift at even lower masses as well? And to look at both of those, we have the PASSAGE survey. This is a cycle 1 pure parallel program with JWST. We observed 63 fields distributed on the sky as shown. 14 of those are in Cosmos, 9 in Cosmos Web. That matters because we need masses for mass metallicity, but we're also following up all the other fields, so we'll have masses for all these fields in the future. And I'm going to just share the new results. The blue, again, are the new measurements. And the orange line here is the result I showed you on the previous slide. We've now increased in redshift. We've gone from around redshift 2 to redshift 3. And you can see the shape seems to not have changed significantly. Modulo at the very lowest mass, we've got now an even lower mass point. Maybe there's something happening there. But keep in mind, I mentioned, if you select galaxies that have higher star formation rates, you're going to have pre-selected for lower metallicity. So we're actually investigating still at this point whether there's a change there or if it's just a star formation rate dependence in our sample. We're also going to look at morphologies. Now, what if you went to even higher redshift? So for that, we have another program, POPPIES, which is a cycle 3 program to use wide-field slit spectroscopy with NIRCam. This allows us to go to longer wavelengths, higher redshifts. Higher resolution means we can potentially also get direct metallicities by stacking, not just strong lines. So this is something else that we're going to be working on and hopefully have results soon. Now, let's go ahead and move and say, can we see these gas flows? So we're back to the Muse Ultra Deep Field. And the histogram is just the galaxies we measured in emission. And then the horizontal bars are the 2 quasars. And we have 3 different colors, one for each metal transition. And we've marked those metals at different redshifts. We match up the galaxies with the gas and absorption. Now we have pairs of galaxies. And then we can look at the orientation of the galaxy relative to the position of the quasar and measure an angle. And the reason this matters is that accretion tends to come in along the major axis and outflows perpendicular to that. And so if you make a histogram of those position angles, you would expect a double peaked distribution. And this is actually a real result from low redshift from Alex Beckett. And so we want to say, can we see this at high redshift where these gas flows are much more prominent? Well, if you just take all the galaxies and you make the histogram, you don't see anything. This is a little disappointing. But then if you go ahead and do subsamples where you say, for example, let me look at galaxies that are low impact parameters, that are close to the gas, or let's look at very high specific star formation rate galaxies. These are galaxies with stronger outflows. Now you get a statistical significant result. So anything below this dashed line is 2 sigma. And so we have tentative evidence that we see evidence of inflows and outflows, but not that satisfying. So what are we going to do next? We're going to increase the sample significantly. So we have a new program with HST and JWST to target 51 quasar fields that have Muse data to do the exact same experiment. But now our statistics are going to be a lot better. So if you look at the figure on the right, we're going to be able to differentiate different models. We're also going to be able to look for evolution with redshift. One of the big changes here, the new result was at high redshift. The old result was at low redshift. So maybe we're witnessing evolution, maybe not. We're also going to be able to do both the H1 gas and the metals together. So stay tuned for this in the future. Now let's connect those galaxies with the CGM gas. Right? And I mentioned damp Lyman alpha systems, and these are special gas systems because they have very high column densities of H1 gas, sufficient such that they're neutral. Okay? And this neutrality is really important. It allows you to measure very robust metallicities as well as a lot of other properties. Also, it dominates the neutral gas content of the universe. So with this data, you can also measure the H1 mass density of the universe. So to connect these, we have a program called CAG, KCWI, Analysis of Gas Around Galaxies. And this is just a survey targeting 36 DLAs in 17 sightlines, so very efficient. And we looked for Lyman alpha emission from the galaxies in KCWI at the redshifts of the DLAs from the quasars. And then we can plot the metallicity of the gas systems against the impact parameter that we show on the right. And if you look at the black points, okay, you'll see that generally, they live between 10 and 100 kiloparsecs. This is the CGM of galaxies. Also very important is previously people have really struggled with these kinds of measurements. We find galaxies associated with DLAs about half of the time. So that's a huge change from handfuls. Okay, so there's a lot of selection that goes into these surveys. And then they also tend to be at lower metallicities. This is also very interesting because there's lots of studies that have found that only when you go after the most metal-rich DLAs you find the galaxies, but we actually find the galaxies at all metallicities. Anyway, our conclusion is that DLAs are predominantly the CGM of galaxies. So now if we study the properties of those DLAs, we're learning about the properties of the CGM. So there's another survey called the QZ5 survey, where we set out to measure the metallicities and the H1 mass density in 61 sightlines with ESI and X-Shooter. And when we did this, we were expecting to detect about 20 DLAs, so we can really measure metallicities at the very high redshift range. We found 6. And this was actually a result in itself, right? If you only find 6, that means the incidence rate of these systems is low. And that's telling you that the H1 mass density at high redshift is lower than you thought. Now, historically, this is a plot of the H1 mass density versus redshift. And what people typically refer to as the blue line on this plot. And a lot of simulations compare to that. And this was a fit where they included all the data. But if you are careful about what signal to noise those days are at and what resolution they had to be able to differentiate multiple Lyman limit systems that could masquerade as a DLA at higher redshifts, and you remove those lower quality data, you see the turnover already in the old data, and then you add our redshift 5 point at the end there in red, and you actually find a nice fit peaking at redshift 3. And this actually makes a lot of sense. If DLAs are the CGM of galaxies, and we know that the star formation rate density and the H2 mass density both turn over at around redshift 2, you'd expect the H1 to do something similar, right? And so there is a process where the DLAs tracing the galaxies are doing the same thing, just at higher redshift, and the fraction of the H1 gas in DLAs as you go to highest redshift must change, because we know the neutral fraction increases out at very high redshifts. Okay, so then the ultimate goal was to measure the metallicity evolution and see to investigate what's happening at the highest redshifts. I'm not going to go into this a lot, but basically we reproduced the results from my previous work from a decade ago. This was with the student Emmy Whites. But a big change here is we applied corrections for alpha enhancement and dust, which we hadn't done in the past. But we find that you still have this nice linear relation in the metallicity. But at the highest redshifts, at redshifts around 5, you see this deviation in the metallicity from the extrapolated trend. And that still seems to be statistically significant, but it's still small number statistics because we were hoping to double the sample and we weren't able to do that. So hopefully we'll understand what's going on there in the future. Okay, and so now my last area is reionization. So we're going back to the galaxies and how they reionize the universe. And so we studied this with another pure parallel program called Pi. And in this case, we targeted 37 independent fields with UV imaging and optical imaging to do color selection to select redshift 3 galaxies. At low redshifts, we found a lot of evidence of Lyman continuum escape from galaxies, and that's why we believe galaxies reionize the universe. But we really want to see this in high redshift galaxies that are more similar to the galaxies that actually reionize the universe early in the universe. The problem is the IGM gets very dense, so when you go back in redshift 3 seems to be a pretty good sweet spot where you can still detect the galaxies, but you're as close as you can get. We have a whole bunch of independent fields because the transmission of the IGM is actually correlated on scales of megaparsecs. What this means is if you just look in Goods North or you just look in the Hubble Ultra Deep Field, all of your galaxies, the IGM transmission is correlated. So if you get an average escape fraction of galaxies, they're all having similar transmissions of the IGM. So you really want to do this on lots of different sight lines, and that's what we're doing here. So in Pi, if you look at the plot on the right, there's a completion versus redshift for different magnitude galaxies. And what we would, in order to measure Lyman continuum from these data, we want that middle shaded orange region. But what we get from the data is the shaded yellow region. And so what that means is we have to follow up with spectroscopic follow-up these galaxies and confirm whether or not they're in the yellow or in the orange region. And if they're in the orange region, we can look for Lyman continuum escape from those galaxies. And that spectroscopic follow-up is happening right now. And then I do want to share with you a Lyman continuum emitter at high redshift because, and so this is new work by Ilias Guverts, where we have found a redshift greater than 4 Lyman continuum emitter. And on the left there, you can see the Lyman alpha line. It's a asymmetric line, just as expected from Muse. And then if you look on the right, we've got the SED of the galaxy in different images. And you can see if you look in 435W, that's a 10 sigma detection. Okay, that's huge. And when you do the SED modeling of this galaxy, the reason why we can see this galaxy at redshift 4 is because it's extremely young. So when you have a very recent starburst, you have a much higher fraction of ionizing photons coming from that galaxy, and that's what's allowing us to see it at redshifts greater than 4. So in summary, I'm a little low on time, but using the spherical cow version of the baryon cycle, we can connect the mass metallicity relation. We find that at redshift 2 and 3, it has a similar shape as at lower redshift, but an offset normalization. We identified how galaxies are associated with DLAs, finding that DLAs are predominantly in the CGM of galaxies. We measured the H1 mass density peaking at a redshift of 3. We looked at the metallicity evolution, and we're searching for Lyman continuum emitting galaxies, and we found one at a redshift greater than 4. Thank you.
Time for a couple of questions from Mark. Yes.
This is an amazing span of work. About the MZR, so the idea that you have gas flows coming in and you're going to have a higher star formation rate, that means that you're diluted.
That's right.
Which way is why it brings lower. So my question is, like, how does that square with, if you have a high star formation rate, your oxygen abundance is going to go right back up, right? When your massive stars expire and return those heavy elements back into the ISM. So, I mean, isn't the timescale for which the dilution happens really short? And how does that get maintained so you can actually see it on the MZR?
So when we look at these high star-forming galaxies, we actually do see this decrease in the metallicity. Right, so we measured, so on the timescales of our measurement that our measurements are making, it's already mixed. And vice versa, I didn't get to share with you because of time, but if you look at our very low redshift points from the Muse Ultra Deep Field, there we're going to much, much lower star formation rates than STSS. And the metallicities are all super high because their star formation rates are so low. So there's not a lot of inflowing gas to dilute what's going on. So you're just producing metals, and that's increasing the metallicity. But if you extrapolate the Sloan results, they match up exactly where we would expect them to. So I guess what I'm saying is that those timescales of mixings have to be short in order for this to work. But it's observed in both directions, we see increases and decreases in metallicity based on the star formation rate. The star formation rates are, of course, measured on longer timescales. So if anything that's happening on short timescales, we are not sensitive to that star formation rate. So that's probably why the timescales of mixing, it has 10 million years or more, because otherwise we don't know the star formation rate.
Thank you for the cartoon. That really makes my day. Love it. Maybe my favorite version now. Connected with Janice's question, for fields where you've done the redshifts with the grisms, you have enough resolution to look at the internal distribution of the metals, the metallicity gradient or some non-parametric measure of the distribution of metals, because we're seeing in simulations that that's actually kind of diagnostic of how the mixing happens and the timescales.
Right. So we want to do that. And we actually said in the proposal we would do that. Not with passage, because the spectral resolution is too low. Sorry, the spectral resolution is okay. Yeah. The spatial, it's very low resolution. So we actually went and looked, and we wrote a paper and looked at the gradients, and the signal and noise of the different lines just degrades once you start breaking up the galaxy. And so if we look at the brightest sources, we have a result. And so that paper is published. There's another paper we're writing right now where we look at a larger set of bright samples. But I think we're just looking at noise. And so we're struggling on this. And I wanted to write a third paper on this, but it's just the sample's not there. The data's not sufficiently high signal and noise. So I think, yes, you can do this on individual systems, but you need extremely deep data if you're going to do this at high redshift. You can do it at lower redshifts, and other people have done that. There's a number of papers on the metallicity gradients. But
comparing to papers that are using nearest for this, so there may be some opportunity there.
Yeah. So we have a paper out with on the passage data looking at that. Ion, he was a former postdoc here.
Same paper.
Oh, okay. So same. Okay. Yeah. So that's with passage data. But those are some of our deepest fields, looking at our brightest galaxies at those redshifts, and so. Yes, you can do it for a very small number, and we wanted to do it for larger numbers.
Okay, let's thank Mark and all of the speakers. Yep. cookies and celebratory champagne outside, so please join. Yay. Perfect.